Hello, let's talk about aromaticity. All right, this is the reason that we were doing all of the review on our resonance structures. Okay, so it's pretty much the most important concept that we're coming across really this semester. All right, aromaticity. Number one, what is it and how to find it? Okay, aromaticity is a very, 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 very special property, okay, in certain unsaturated molecules that have delocalized electrons, okay. They are cyclic, planar, and contain a specific amount of pi electrons. And this special arrangement means they are held tighter than those in non-aromatic systems. Okay, blah, 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 blah. I'm going to come back to these words, but I want to talk about our conditions down here. Number one, if you want to be aromatic or extra, extra stable, okay, it has to be cyclic, it has to be conjugated, it has to be planar, and you have to have a special number of electrons, a special number of electrons. All right, now the cyclic, I hope, is just a dead giveaway nowadays. We've done enough systems. Hey, look, it's cyclic. That one's not. Okay, so literally there's nothing special about that. It has to be cyclic. It has to be conjugated. Benzene is the one that we always played with in the past because it was cyclic and conjugated, where this one is not conjugated. So we wouldn't even consider either of those two to be aromatic because they don't match two of the conditions. Mm, Planar is a little harder because the last time I showed you that planar, I showed you that puckering one. Okay, some of these are difficult to visualize because you just don't expect them to pucker. All right, but it does have to be perfectly planar. And then you have to have the correct number of electrons, and it's called the Hugel number. All right, so for example, 4n plus 2 equals the number of pi electrons, but you can't have fractions. Okay, you can't have fractions if you solve that algebra equation. So 4n plus 2 is equal to 4. Subtract 2 from both sides, and you get 4n is equal to 2. So n is equal to 1/2. So no. Okay. Generically, it has to be a whole number integer. Okay. So we're just going to keep going and going and going with those. Now, before I show you some examples, I'm going to tell you about the variations. All right, so we can have complete carbon rings, also called annulenes. We can have ions, and we can have heterocyclics. And this video is just going to talk about our carbon rings, or these things called annulenes. All right, what are my choices here? I can be non-aromatic, which means it doesn't even consider one of the conditions. Okay, it just doesn't even match one of them. You can be aromatic, which means all of them are perfect, or you could be anti-aromatic, which means you are not being the perfect arrangement. And so we are going to be talking about, where do I write that down for you? The number of electrons right here. So if it's all there except the correct number of electrons, we call it anti-aromatic. All right, let's build up. The first cyclic system that we can have is cyclopropane. So number one, is it cyclic? Yes. Number two, is it conjugated? No. Okay, it's just not aromatic. Okay, it doesn't even match the second condition. All right, let's do cyclobutene. Actually, butadiene, because there's two of them. All right, is it cyclic? Yes. Is it conjugated? Yes. Is it planar? Okay, now that one's tougher, but let's assume yes. Let's check those electrons. All right, how many electrons am I considering Remember, only the electrons in the pi system. So when I say the pi electrons, I'm only talking about those that are delocalized. So there's 4. So let's check our numbers. 4n plus 2 is equal to 4. So n is equal to 2 over 4, or 1/2. And guess what? The big ol' answer is wah. But it matched all the conditions except that one. So we would call this anti-aromatic. Now, don't forget that we did assume that. Okay, but that's a variable that we're going to consider by itself. All right, so there was 3, there was 4, here's 5. Okay, that is like completely ugly looking. Could draw it there. That one's prettier. Okay, same molecule. All right, number 1, is it cyclic? Yes. Number 2, is it conjugated? Nope. That is an sp3 carbon. So guess what? It's just non-aromatic or not aromatic. Keep going. All right, number 1, is it cyclic? Yes. 2, is it conjugated? Yes. And remember, conjugated means does everybody have a p orbital? 3, is it planar? And this one I don't even have to assume because benzene is completely flat, sp2 hybridized around. And 4, does it have the correct number of electrons? Switch colors. Let's try green. All right, so 4n plus 2 equals, we have 6 electrons in our system. So 4n, so subtract 2 from each side, is equal to 4. So n equals 1. That is a whole number. So yay! This one is aromatic. Why do we care? That one is exceptionally stable, more so than what we would have expected. More so than what we would have expected. Jump over to the whiteboard to continue on. All right, so that was 6. Should have just started over here, I guess. One, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, and 8. Okay. 1, 2, 3, and 4. Remember, 1 is cyclic. Should have left myself more room. Cyclic, conjugated. Let me see, cyclic, conjugated, planar, and Hugel electrons. So we said yes, yes, and, oh, sorry, so yes and no. We said yes, yes, yes. This was our little assume. And no. So this one is just non or not. This one was anti. This one, planar yes, but it was not conjugated, so it's non or not. This one is aromatic. All right, this one is cyclic, but, oh, look, there's an sp3, just like those other members. So, wah. So this one's just non. Okay, now this one's interesting. Yes, it's cyclic. Yes, it is conjugated. Okay, now here's a big question. We're going to talk about that planar in a minute. So let's just assume this thing turns out to be flat. Does it have the correct number of electrons? And 1, 2, 3, 4. So 4 times 2 is 8. So 4n plus 2 is equal to 8. Subtract 2 from both sides. So 4n is equal to 6, and n is equal to 6. fourths or 3/2. Ah, okay. This one is anti. So even if it was flat, okay, and we didn't even really go into that issue, even if it was flat, it doesn't have the correct electrons. But if it's not flat, we would have said it was non. All right, so we are going to have to consider that flat issue. But assuming it is flat, it would just be consider anti. Oh, look, there's kind of a trend. So the next one, which is hard to draw, would be 9 and then 10. Let's see if I can draw 'em. 1, 2, 3, 4. Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that is so ugly. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I did that correctly. And right there. Oh, look. Is it planar? Yes. Is it conjugated? No. Nah. But this one is the one I drew for you before. All right. Yes, it's planar. Yes, it looks conjugated. All right. Is it planar? Okay, we're going to do a little assume. We're going to assume that it is. Let's check those electrons. So we have 2, 4, 6, 8, and 10. So 2, nope, sorry, not 2n, 4n. 4n plus 2 is equal to 10, so subtract 2. So 4n is equal to 8, so n is equal to 2. Yay! So this is yes, if. Okay, so it is aromatic if it's planar. But guess what I told you? Those two hydrogens, they just get in the way. It puckers. So this condition fails. So even though we have that wonderful number of electrons, this one fails. And by our rules, if it fails any of the above 3, this one would be called, oh, sad. Now this one would just be non-aromatic. All right, go back to our notes. All right, that was a very, very, very short, but very, very, very important video. All right, aromaticity. Very special molecules that are exceptionally stable. Benzene is the one that we have seen and used in the past. There are other molecules that also fall into that category. They are, I can't even stress it, exceptionally stable, and therefore they do some unique chemistry. All right, how are you going to determine whether they are going to be aromatic? They must match all the conditions. So let me see. You know what? Let's just go down here. They must be cyclic. They must be conjugated. They must be planar. I think that's actually the hardest one. And then they must have this correct arrangement or number of electrons called the Huckel number. And for me, the best way to do the Huckel number was when I solve for n. If it comes out a fraction, the answer is no. And if it comes out a whole number, the answer is yes. Look out for those sp3 hybridized carbons that are hidden inside of a system. And then the annulenes, or the carbon rings, if you'll notice, are just carbons. And so we went all the way up through number 10 and saw all the variations. We're also going to play with some ions and then some heterocyclics. But for this one, that was just dealing with the aromaticity of the annulenes. All right, until next time, jolly out.